All right. We have come a long way from turning our image into a patch embedding with equation 1, replicating the multi-head self-attention block with equation 2, and doing the same thing with the multi-layer perceptron block for equation 3, creating the transformer encoder. Do we have all of the pieces of the puzzle for creating the overall vision architecture, vision transformer architecture, that is? You might be wondering, hey Daniel, we're missing the MLP head, and we haven't done equation 4. And you're 100% right, but equation 4 is going to look like a breeze compared to what we've done with all of these. If we go up here, if we read, what do we have? The classification head, or the MLP head, is implemented by an MLP, so a multi-layer perceptron, with one hidden layer at pre-training, so a linear layer, and by a single linear layer at fine-tuning time. So all we need for the MLP head is a layer norm layer and a linear layer to project to the number of classes that we have. But no point talking about it, let's code it out. We'll jump into here and let's create section 8. We're going to put all of the pieces of the puzzle together, the inputs, the outputs, the layers, the blocks, everything we've been talking about. Putting it all together to create VIT. Now, you might want to pause the video now and give it a shot yourself before we go through it together, because we've got all the pieces of the puzzle ready, and I think you're very capable of doing it yourself now. But if you want to follow along, I'm going to start in 3, 2, 1. So the first step is to create a VIT class. So we're going to use the VIT class to inherit from nn.module. So we get all the benefits of what's going on behind the scenes in nn.module. And then we're going to initialize it much like we have all of our other code blocks. And the VIT module, the VIT class, is going to put together, it's going to pull everything together that we've done so far. So self, we're going to put in the image size here. And most of these hyperparameters or parameters are going to be ints. So we'll set a default to 224 because that's the same size as the paper. And I'll just write here. I'm trying to reference things where I can, so you can look it up if you want to read more. Table 3 from the VIT paper. And then we'll go in channels. Now we've done this a fair few times now. In channels is going to be what? 3 by default, because we're dealing with color images. The patch size, well, we've been working with a patch size of 16. Of course, you could change that if you want, but we want the patch size to be compatible with the image size. So we might put an assertion for that later. Now, number of transformer layers, we haven't seen this one before, but we'll put it together in a second. So this is going to be 12. Now this is the number of layers. This is table, I'm just going to put this as a comment, table 1 for layers. Layers for VIT base. So we're starting with the smallest version of VIT so that we can scale up later if needed. So table 1, layers equals 12. So layers refers to the number of transformer encoder blocks. So transformer encoder, we've turned that into a pytorch code block. So we'll be able to stack on top of each other 12 of these to create the overall architecture. That's what happens inside here. So this goes inside here and gets stacked on top of each other LX times. We'll keep going here. What else do we need? Well, of course we need our embedding dimension, which is an int. Embedding dimension could actually probably come earlier because it's so important, but the order here doesn't really matter. So this is hidden size D from table 1 for VIT base. Again, we could change this if we wanted to scale to VIT large or VIT huge. MLP size, this is going to be an integer, and I'm going to set this by default. That's going to be the hidden unit size within our MLPs. So that's 3072. Then we'll go a number of heads in the multi-head attention, and that is again from table 1. Both of these are from table 1. Beautiful. And what are we up to next? How about we do the dropout? So attention dropout is going to be 0 because the paper doesn't actually mention having any attention dropout. So if we look again, we go dropout. We need, dropout when used is applied after every dense layer. So in our MLP, except for the KQV projections. So what are the KQV projections? Well, that's our multi-head attention, right? Because another word for self-attention or multi-head attention is KQV attention. and that's up here. Standard KQV self-attention. So we'll keep going. We need now MLP dropout. There is a little bit of dropout for the MLP. Recall that dropout is a regularization factor. So it randomly removes connections between layers to hopefully make the remaining connections better. And then we go here. Finally, we'll set an embedding dropout, because another little treasure of the paper is that there's also an embedding dropout. So this is dropout for patch and position embeddings, where of course we can read that back up here. Dropout, when used, is applied after every dense layer except for the KQV projections and directly after adding the positional to patch embeddings. So we'll see this in the forward method of our VIT. We come back. We've got a lot of hyperparameters here, but the last one we need is a number of classes. So this is going to be the number of classes in our classification problem. And I've set this by default to be 1,000. Why is that? Well, that's because the original VIT architecture was trained on ImageNet, so it's going to have 1,000 classes. Whereas in our case, we're working with pizza, steak, and sushi images because we're using VIT for Food Vision Mini, so we would have 3. But I'm going to set it as 1,000 by default. Woohoo! Look at that. Well, in the words of Lau Tensor, the building of a deep neural network, aka VIT, starts with the first layer, or in our case, it starts with the initialization function. So let's create the super method. Super.init. We'll go there, and time to start it off. So what's first? How about we make an assertion here? Make an assertion that the image size is compatible with the patch size. So we've done this before, but we're going to do it again just to make sure here. Assert image size is divisible by patch size equals 0. And if this doesn't work, we'll go here. Image size must be divisible by patch size. And then we'll go image size is image size, and then patch size is patch size. Wonderful. And then we can keep going here. Or maybe does this need to be spaced over? It does. So we need to tab that over, make sure the lines are in line here, because we've got a fair few parameters here. The spacing kind of threw me off. Now we'll get the number of patches. So we need to calculate the number of patches so that we can use it for creating our position embeddings. So we can do this by going calculate the number of patches. Now we can actually probably do this within the patch embedding layer. And I've said this a few times now, the few steps that we're doing. So that might be an extension. Your first extension would be to incorporate, calculate the number of patches, the class token, and the position embedding all within the patch embedding layer. So we'll go self num patches equals image size, because our image is going to be a square. So basically doing height times width divided by the patch size to the power of 2. And where does that come from? Well, that's the value for n. If we go back to where equation 1 is defined, I'm going a little bit faster here because a lot of this stuff we've covered before. We're just putting it all together. N, here we go. That's how we're calculating n. N number of patches equals height times width divided by p squared. And so we'll keep pushing forward. What should we do next? Well, let's start with the class embedding, hey, right at the front. Create learnable class embedding. So needs to go at front of sequence of patch embeddings. So we've seen this in equation 1. So self.class embedding can be, this is actually a learnable token. And then we'll go data equals torch.randn. Remember how we created it with ones to begin with? Well, now we're creating it with random. Initialize it as a random number and then optimize it using gradient descent. And then finally, we'll set requires grad equals true. This is the default parameter for nn.parameter, but we're just setting it just so that we can see it and for completeness. So the class embedding is going to have a shape of 1, 1 embedding dim, because if we go back here, we are putting the class embedding right at the front of our patch embeddings. So let's keep pushing forward. What else should we do? So we want to, maybe we create the position embedding now. Create learning position embedding. Yeah, these are the steps I'm talking about that could potentially be incorporated into our equation 1. So yeah, the layer we created in 4.8 could potentially contain all of these steps. That would make the vision or the VIT class a little bit smaller. But that's all right. Once we do the full version, refactoring is some good practice. nn.parameter, and then the data here is going to be torch randn. We'll create it as a random variable as well. 1 for batch size, and then we'll go here, self.numpatches plus 1. That's why we created self.numpatches up there. And then we'll pass in the embedding dimension. Beautiful. And then we'll keep going. So we'll create the embedding dropout value. So this is what we just looked at before. If we go into dropout when used is applied after every dense layer except in the attention mechanism, so the KQV projections, and directly after adding positional to patch embeddings. So because we're working on the patch embeddings, we'll create the embedding dropout here. Self.embedding dropout equals nn.dropout, and the p-value here is going to be our embedding dropout parameter above. So this one here. Beautiful. Now what's next? Well, we've got all the pieces of the puzzle around the patch embedding, namely the class token, the position embedding, the embedding dropouts. How about we create our patch embedding layer? So we'll go patch embedding layer. This is going to be our biggest block of code yet, but nothing we can't handle. We're replicating a state-of-the-art machine learning research paper right here. So patch embedding, we'll call it equals patch embedding, and we can set the hyperparameters here as in channels equals in channels. Then we can go patch size equals patch size. And then finally, the embedding dimension here is, of course, going to be our embedding dim, which by default will be 768. So there's our patch embedding. So again, my little extension challenge to you is to see if you can incorporate all of this in the patch embedding layer. That'd be a good extension. Now, what are we up to? Well, we can create the transformer encoder block. So what we want to do here is we've got a class. Let's go back to figure 1. We want the first, yeah, there we go. So we've got a class that incorporates one of these. However, we've spoken about how the transformer encoder here is actually 12 of these in the case of VIT base on top of each other. So you might have done some research and figured out how to stack these on top of each other, but if you haven't, I'll show you a way that you can do that in PyTorch. So we can go self.transformer, I'm going to call it transformer encoder. And so I'm going to use nn.sequential, and watch this little trick. We can use star, which means all, and then create a list comprehension. Yeah, this is some magic right here. Transformer encoder block, which is the layer that we created before in section 7.1. And then we can pass in the different parameters that it requires. So embedding dim equals embedding dim. Then we'll go to the next one. Number of heads for number of attention heads. Num heads. And what else do we have? We have MLP size. We've got this as a variable equals MLP size. And then finally, we have MLP dropout, which equals MLP dropout. Now, all of these parameters I've gathered from up here. So MLP dropout, and then what else do we have? Number of heads, embedding dimension, beautiful. And so now we've got this, we can turn it into for underscore, because we don't need the iterator, we'll turn it into a range num transformer layers, which is another parameter. So that is here. So what we're doing here is we're creating a list of 12 transformer encoder blocks, and then turning that list into its own sequential series of layers using the star parameter or the star syntax, which means all of the layers in this list comprehension. Turn it into a sequential. And that is giving us a way to stack these on top of each other. And then of course, we could do a bigger stack by changing this parameter up here. So there's our transformer encoder block. And what are we going to finish off here? Well, we're up to equation 4. This is the MLP head. We've just built all of this. We have to make the MLP head. And this is one of the easiest ones of the whole architecture. So this is equation 4, y equals layer norm. Now this is a little bit of a tricky one here. The z zeroth of the last layer. So the 0th index of z for the last layer. This is why the figure has an arrow only on the last token here. So that's the classification token. So we only want to pass the classification token through the MLP head. We'll see what that looks like in code in a second. But if we come down, this is described here. The classification head is implemented by an MLP with one hidden layer at pre-training time and by a single linear layer at fine-tuning time. But equation 4 also shows a layer norm. So I'll show you how we can do both of those with PyTorch code. So create classifier head. I'm going to call this self.classifier equals nn.sequential, the handy sequential coming into play here again. Then we'll go nn.layerNorm, which will be the layer norm, ln of equation 4. We've seen that before throughout the MLP block and the MSA block. And we need a parameter here, which is normalized shape. We're going to set that to the embedding dimension that we've been using throughout the entire architecture. And then finally, we have nn.linear. And we have inFeatures equals embedding dimension. Why is that? Well, because the output of the transformer encoding block is going to have a dimension size of embedding dim. So that's going to be the input size to the linear layer. And then finally, since this is the output layer, we've made it all the way to the end. How many out features do we need? Well, how many classes do we have? So let's set this to num classes. So by default, it's going to be 1,000, but of course we could change that to suit our own problem. Oh my goodness. We have built together all of the pieces of the puzzle of the Vit architecture. Now, how about we do the forward method? In fact, why don't I leave this as a challenge to you to prevent this video from getting too long? See if you can put all of these together to create the forward method of the Vit architecture. Def forward self, it's going to take some sort of input. So we've got the class embedding, the position embedding, embedding dropout, the patch embedding layer, the transformer encoder block, and the classifier head. See if you can put them together to replicate the overall vision transformer architecture in the forward method. Give it a shot and we'll do it together in the next video. This is so exciting. I'll see you there.